Hello, in this lecture we will find the area of a circle. In the drawing we have a circle, and inside the circle we have a shape. This angle equals to 90 degrees, angle ADC is a right angle, it equals to 90 degrees, and also angle BCD equals to 90 degrees. Side AD of the shape equals to 4 units. Side DC of the shape equals to 6 units. And side BC of the shape equals to 8 units. And we want to find out the area of this circle. First of all, we will define the term one-sided angles. What are one-sided angles? Actually, if we have two lines, line A this is line A, and this is line B, and line C that intersects those two lines. Line C in the red color intersects line A at this point, while line C intersects line B at this point. Angles alpha and beta are defined as interior one-sided angles. Okay, those angles alpha and beta are defined as interior one-sided angles. I will write it down. Angles alpha and beta are interior one-sided angles. Okay, angles alpha and beta are defined as interior one-sided angles. Why angles alpha and beta are defined as one-sided angles? The answer to that question is because of the fact that angles alpha and beta are located at the same side of line C. Both of them are located at the left side of line C. For that reason they are defined one-sided angles, because both of them are located at the same side of line C. Both of them are located at the left side of line C. And Y angles alpha and beta are defined interior angles. the answer to that question is very simple, because of the fact that angles alpha and beta are located inside the structure of lines A, C, and B. They are located inside this structure of lines A, C, and B. They are defined as interior angles. And actually we have second types of angles, of one-sided angles. We have also exterior one-sided angles. If we have two lines, line A and line B, this is line B, and line C that intersects those two lines. Line C in the red color intersects line A and B. Angles alpha and beta, those two angles alpha and beta are defined as exterior one-sided angles. I will write it down. Angles alpha and beta are defined as exterior one-sided angles. Okay, angles alpha and beta are defined as exterior one-sided angles. Again, they are defined as one-sided angles because both of those angles alpha and beta are located on the left side of line C. Both of those angles are located on the same side of line C. They are both located at the left side of line C. For that reason, they are defined as one-sided angles, and they are defined as exterior angles because of the fact that angles alpha and beta are located outside of the structure of lines A, C, and B. They are located outside of this structure of lines. Therefore, they are defined as exterior angles. Okay, so those two angles alpha and beta are defined as exterior one-sided angles. Okay, and while those two angles alpha and beta are defined as interior one-sided angles, we actually have a rule number 1 about one-sided angles. Rule number 1 states that if the sum of the two one-sided angles and it can be interior or exterior. Okay, I will add interior or exterior. It applies to both types of one-sided angles, interior one-sided angles, or exterior one-sided angles. If the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B. I will read rule number 1 again. Rule number 1 states that if the sum of the two one-sided angles, and they can be interior angles or exterior angles, if the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B. So actually in this drawing, if the sum of two one-sided angles, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Okay, if the sum of those two angles, alpha and beta, equals to 180 degrees, then line A is parallel to line B. And it is also true for exterior one-sided angles. Those angles are exterior one-sided angles, and if the sum of those two exterior one-sided angles equals to 180 degrees, then line A is parallel to line B. And it also true for interior one-sided angles, those two interior one-sided angles. If the sum of those two angles, alpha and beta, equals to 180 degrees, then line A is parallel to line B. Okay, if the sum of those two interior one-sided angles equals to 180 degrees, then line A is parallel to line B. Okay, So we actually can implement rule number 1 in our circle. Because in our circle we have two angles that are right angles. This is a right angle and also this is a right angle, and they are actually interior one-sided angles. Why are they interior one-sided angles? Because they are both located in the left side of line segment DC. For that reason they are defined as one-sided angles, and they are inside the structure of line segments, therefore they are defined as interior angles. So those two one-sided interior angles, the sum of those two one-sided interior angles equals to 90 degrees plus 90 degrees equals to 180 degrees. Therefore, according to rule number 1, line segment AD is parallel to line segment BC. Okay? Actually, you can view line segment AD as line A, line segment BC as line B, and line segment DC is line C that intersects those two lines. And when you view this line segment as A, B, and C, then you can see that those two angles are actually one-sided interior angles. Okay? So angle ADC, the sum of angle ADC plus angle BCD angle ACD equals to angle ADC equals to 90 degrees. It is a right angle. It is given us in the question. And angle BCD also is a right angle. It equals to 90 degrees. So the sum of those two right angles equals to 180 degrees. And as I already told you, those two angles are one-sided interior angles. Okay? And they are one-sided interior angles. So we actually have here two one-sided interior angles that the sum of those two one-sided interior angles equals to 180 degrees. Therefore, according to rule number 1, line segment AD is parallel to line segment BC. Okay, and write it down. Therefore, according to rule number 1, line segment AD is parallel to line segment BC. So I'll read again the things that I wrote. Angle ADC equals to 90 degrees. This is a right angle. It is given us in the question. And angle BCD also equals to 90 degrees. This angle is also a right angle and it equals to 90 degrees. So the sum of those two angles equals to 180 degrees. And those two angles are one-sided interior angles. That the sum of them is 180 degrees. So therefore, according to rule number 1, rule number 1 states that if the sum of the two one-sided interior angles equals to 180 degrees, then line A is parallel to line B. So we have two one-sided angles that the sum of them is 180 degrees. Then therefore, according to rule number 1, line segment AD is parallel to line segment BC. Line segment AD is parallel to line segment BC. Okay? So in the next step, we will connect together points B and D by a straight line. And we will also connect together points A and C by a straight line. And we will call to the intersection point between line segment BD to line segment AC point O. Again, point O is the intersection point between line segment BD to line segment AC. Okay? And we will define a new term of vertex angles. Actually, if two lines are intersecting each other, For example, if line A intersects with line B, this is line B. So if two lines, line A and line B, are intersecting each other, actually this is the intersection point, and at the intersection point, at this point, they create four angles. This is angle number 1, this is angle number 2, this is angle number 3, and this is angle number 4. So when two lines are intersecting each other at the intersection point, they create four angles: 1, 2, 3, and 4. Actually, angles 1 and angles 3 are defined as vertex angles, and according to a new rule, rule number 2, they are equal to each other. Okay, I write it down. Angles 1 and 3 are defined as vertex angles. Those two angles are defined as vertex angles. And according to a new rule, rule number 2, they are equal to each other. Angle 1 equals to angle 3. According to a new rule that I will write down immediately. Okay, so angles 1 and 3, those two angles are defined as vertex angles, and according to rule number 2, they are equal to each other. That is to say, angle 1 equals to angle 3, and also angles 2 and 4 are also defined as vertex angles, and according to rule number 2, they are equal to each other. So I'll write it down. Angles 2 and angle 4 are also defined as vertex angles. And according to rule number 2, they are also equal to each other. Okay, so angles 2 and 4 are also defined as vertex angles. Those two angles in the red color, angles 2 and 4, are defined as vertex angles, and according to rule number 2 they are also equal to each other. So now I'll write down rule number 2. Rule number 2 states that vertex angles are equal to each other. Okay? According to rule number 2 states that vertex angles are equal to each other. So I will read rule number 2 again. Rule number 2 states that vertex angles are equal to each other. So here in the drawing we have two vertex angles. As I already told you, angle 1 and 3 are defined as vertex angles and they are equal to each other according to rule number 2. And angle 2 and 4 are also vertex angles and they are also equal to each other. Now I will draw the two pairs of vertex angles. Angle 1 and 4 is the first, angle 1 and 3 is the first pairs of vertex angles, and angle 2 and 4 are the second pair of vertex angles. I will draw them separately. So if we have two lines that are intersecting each other, line A intersects with line B. This is the intersection point between line A and line B. Those two angles are defined as vertex angles, and according to the vertex angles and according to rule number 2 they are equal to each other. That is to say, alpha equals to beta according to rule number 2. Okay? Those two angles are vertex angles, and according to rule number 2 they are equal to each other. And the second pair of vertex angles this is line A, this is line B. Okay, so angles alpha and beta, those two angles are also defined as vertex angles. They are also vertex angles. And according to rule number 2, they are also equal to each other. Alpha equals to beta according to rule number 2. Okay, so we actually have two pairs of vertex angles. If this is the first pair of vertex angles that are equal to each other according to rule number 2, then those vertex angles are the second pair of vertex angles, and they are also equal to each other according to rule number 2. So those are the first pair of vertex angles that are equal to each other, and those two angles are the second pair of vertex angles that are equal to each other according to rule number 2. Okay, so we actually can implement rule number 2 in our drawing. Actually, those two angles are defined as vertex angles, and according to rule number 2 they are equal to each other. Okay, those two angles are defined as vertex angles, and they are equal to each other according to rule number 2. I write it down. Angle AOD, this angle, equals to angle BOD, to this angle, because of the fact that those two angles are vertex angles, and according to rule number 2 they are equal to each other. Okay, angle AOD equals to angle BOD. Those two angles are equal to each other because of the fact that they are vertex angles, and according to rule number 2 vertex angles are equal to each other, so they are equal to each other. Okay, and in the next step we will define the theorem of alternating angles. What are alternating angles? Actually, if we have two lines, line A this is line A, and line B, this is line B, and line C that intersects those two lines, line C in the red color intersects those two lines. This is the intersection point between line C and line A, and this is the intersection point between line C and line B. Angles alpha and beta those two angles are defined as interior alternating angles. Okay, those two angles alpha and beta are defined as interior alternating angles. I will write it down. Angles alpha and beta are defined as interior alternating angles. Okay, those two angles alpha and beta are defined as interior alternating angles. First of all, why are the angles alpha and beta are alternating angles? The answer to that question is very simple, because of the fact that those two angles alpha and beta are located at different sides of line C. They are defined as alternating angles, while angle alpha is located to the left of line C, angle beta is located to the right of line C. So they are located at different sides of line C. For that reason, they are defined as alternating angles. Okay, and why are they defined as interior angles? The answer to this question is very simple, because of the fact that those two angles are located inside the structure of lines A, C, B. They are defined as interior angles. They are located inside the structure of lines A, C, B, inside of this structure of lines. For that reason, they are defined as interior angles. Okay, and we also have a second type of alternating angles, the exterior alternating angles. Actually, if we have two lines, line A and line B, and line C intersects those two lines, line C in the red color, this line intersects those two lines. Angles alpha and beta, those two angles alpha and beta are defined as exterior alternating angles. Okay, I write it down. Angles alpha and beta are defined as exterior alternating angles. Okay, angles alpha and beta are defined as exterior alternating angles. And again, the reason that they are defined as alternating angles because of the fact that they are located at different sides of line C, while angle alpha is located to the left side of line C, angle beta is located to the right side of line C. So they are located at different sides of line C. For that reason, they are defined as alternating angles, and they are also defined as exterior angles because of the fact that both of those angles, alpha and beta, are located outside of the structure of lines ACB. They are located outside of this structure of lines ACB, therefore they are defined as exterior angles. So those two angles are defined as exterior alternating angles. Okay? And those two angles alpha and beta are defined as interior alternating angles. Okay? We actually have a rule number 3, about alternating angles. Rule number 3 states that alternating angles between parallel lines are equal to each other. So I will read rule number 3 again. Rule number 3 states that alternating angles between parallel lines are equal to each other. And it doesn't matter at all if they are interior alternating angles or exterior alternating angles. So I will add here that they can be both interior or exterior. Interior or exterior alternating angles between parallel lines are equal to each other. Okay, I'll read rule number 3 again. Alternating angles and between parallel lines are equal to each other. So actually if we know that line A is parallel to line B, if line A is parallel to line B, then according to rule number 3, angle alpha equals to angle beta. Okay, so if we know that line A is parallel to line B, then and only then angle alpha equals to angle beta. So if line A is parallel to line B, those two angles are equal to each other. Okay? And the same rule applies also to those interior alternating angles. If line A is parallel to line B, then those two angles are equal to each other. So I write it down. If line A is parallel to line B, then those two angles are equal to each other. That is to say, angle alpha equals to angle beta. Okay, so if those two lines are parallel to each other, then the angles are equal to each other. If line A is parallel to line B, then angle alpha equals to angle beta. Okay? So we will implement rule number 3 in our drawing. First of all, we will focus on triangles POC and triangle AOD. We will focus on the green triangle BOC, and on the green triangle AOD, the small green triangle AOD. Okay, so I write it down. We'll focus on the green triangle, big green triangle BOC. And the small green triangle AOD. Okay, so on these two green triangles, those two angles are equal to each other. Angle AOD equals to angle BOC. We have already talked about it, that those two angles are vertex angles, and according to rule number 2, they are equal to each other. So I'll write it down. Angle AOD equals to angle BOC. The angles that are marked in the red color, those two angles are equal to each other because they are defined as vertex angles. And according to rule number 2, they are equal to each other. Okay, angle AOD equals to angle BOC because of the fact that those two angles are defined as vertex angles, and according to rule number 2, they are equal to each other. Okay, and actually angle DAO, this angle equals to angle BCO, so this angle. Okay, so those two angles are equal to each other because of the fact that those two angles are defined as alternating angles, and they are located between parallel line segments. Line segment AD is parallel to line segment BC, and according to rule number 3 that states that alternating angles between parallel lines are equal to each other, those two alternating angles that are located between parallel lines are equal to each other. So I write it down. Angle DAO, this angle, equals to angle BCO. Because they are alternating angles. Why are they alternating angles? Because they are located at different sides of line segment AC. Okay, they are located at different sides of line segment AC, and they are located between parallel line segments. Line segment AD is parallel to line segment BC according to rule number 1. So they are two alternating angles that are located between parallel line segments, therefore they are equal to each other according to rule number 3. Okay, so angle DAO equals to angle PCO because they are alternating angles. And they are located between parallel line segments. Line segment AD is parallel to line segment BC according to rule number 1. So alternating angles according to rule number 3 between parallel line segments are equal to each other. So those two angles are alternating angles that are located between parallel line segments. Line segment AD is parallel to line segment BC. So therefore they are equal to each other according to rule number 3. Okay, so angle DAO equals to angle BCO. Those two angles are equal to each other because they are alternating angles and they are located between parallel line segments. Therefore, according to rule number 3, they are equal to each other. Okay. And angle CBO, this angle equals to angle ADO, to this angle. So those two angles are also equal to each other because those two angles are actually alternating angles. They are located at different sides of line segment BD and they are located between parallel line segments. Line segment AD is parallel to line segment BC, so they are actually alternating angles that are located between parallel line segments. Therefore, according to rule number 3, they are equal to each other. Okay, so I write it down. Angle ADO is equal, this angle equals to angle CBO because they are alternating angles. They are located at different sides of line segment DB. So they are alternating angles. And those two alternating angles are located between parallel line segments. Line segment AD is parallel to line segment BC. Therefore, according to rule number 3, It states that alternating angles between parallel line or parallel line segments are equal to each other. They are equal to each other. Okay? So angle ATO equals to angle CBO. Those two angles are equal to each other because they are alternating angles and they are located between parallel line segments. Therefore, according to rule number 3, they are equal to each other. Okay? Again, rule number 3 states that alternating angles between parallel line segments are equal to each other. So those two angles are alternating angles and they are located between parallel line segments. Line segment AD is parallel to line segment BC. Therefore, according to rule number 3, they are equal to each other. So we actually proved that those two angles are equal to each other. Also, those two angles are equal to each other, and those two angles are equal to each other. So we proved that 3 angles of this green triangle are equal to 3 angles of this green small triangle. Therefore, we proved that those two green triangles are similar to each other according to the rule of angle, angle, angle. When you prove that 3 angles of one triangle are equal to 3 angles of another triangle, you actually proved that the triangles are similar to each other. Okay? So I write it down. We proved that the big green triangle BOC is similar to the small green triangle AOD. According to the rule of angle, angle, angle. When you prove that 3 triangles of one triangle are similar to 3 triangles of the other triangle, you actually prove that those 2 triangles are similar to each other. Okay, according to AAA, A is relation to angle. According to angle, 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 those 2 triangles are similar to each other. Okay, so triangle BOC, the green big triangle, is similar, that is the sign of similar to triangle AOD, to this small green triangle, according to the rule of angle, angle, angle. Whenever you prove that 3 angles of one triangle are equal to 3 angles of the other triangle, you actually prove that those 2 triangles are similar to each other. And when 2 triangles are similar to each other, they have a special relationship between their sides. Okay? If we have, for example, 2 similar triangles, if triangle ABC is similar to triangle DEF. Okay, if those two triangles are similar to each other, then the following relationship between their sides are true, that AB over ED equals to AC over DF equals to BC over EF. Again, AB over ED equals to AC over DF equals to BC over EF. So I write it down. AB over ED equals to AC over DF equals to BC over EF. Okay, so if those two triangles are similar to each other, then the following equality is true, that AB over ED equals to AC over DF equals to BC over EF. Okay, and we proved that in our drawing that the green triangles are similar to each other, so the following relationship is true in our two green triangles, that OB over OD equals to OC over OA equals to BC over AD. Again, OB over OD equals to OC over OA equals to BC over AD. Okay, OB over OD, OB over OD equals to OC over OA equals to OC over OA equals to BC over AD. Okay, but we know that BC equals to 8 units and AD equals to 4 units. Okay, so you can write here that BC equals to 8 units and AD equals to 4 units. And 8 over 4 is 2. So in total we got the equality that OB over OD equals to OC over OA all equals to 2. Okay, so from this equality we can derive two equalities. The first equality that we can derive from this big equality, that OB over OD equals to 2. Okay, OB over OD equals to 2. So I write it down. Okay, OB over OD equals to 2. if OB over OD equals to 2, we can multiply this equality by OD. We will get that OB equals to 2 times OD. Okay, we multiply this equality by OD. We got that OB equals to 2 times OD. So OB equals 2 times OD. So if OD equals to A, then OB equals 2 times OD. OB equals 2 times A, because OB is twice as large as OD. So if OD equals to A, then OB will be equal to 2 times A. Okay? And the second equality that we can derive from this big equality is that OC over OA equals to 2. Okay, OC over OA equals to 2. I'll write it down separately. OC over OA equals to 2. So OC over OA equals to 2. We can multiply this equality by OA and we will get that OC equals to 2 times OA. OC equals 2 times OA. So actually, if OA equals to B, then OC equals 2 times OA. OC equals 2 times OA, so, and we know that OA equals to B, so OC will be equal to 2 times B, because actually OC is twice as large as OA, and we know that OA equals to B, so OC will be equal to 2 times B. Okay? And in the next step we will find out the values of A and B, and we will use the Pythagorean theorem in order to find out the values of A and B. First of all, angle ADC is a right angle. It is given us in the question. It equals to 90 degrees. Angle ADC equals to 90 degrees. So if angle ADC equals to 90 degrees, then triangle ADC is a right triangle. Okay, triangle ADC is a right triangle. And if triangle ADC is a right triangle, then we can implement the Pythagorean theorem in the right triangle ADC. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, the square of the hypotenuse in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ADC, the square of the hypotenuse is AC square. Equals to the sum of the squares of the perpendiculars equals to AD square plus DC square. Again, in the right triangle ADC, we implemented the Pythagorean theorem that states that the square of the hypotenuse, that is to say AC square, because AC is the hypotenuse in the right triangle ADC, equals to the sum of the squares of the perpendiculars, equals to AD square plus DC square. Okay? But what is the value of line segment AC? AC equals to OA plus OC, or AC equals to AO plus OC, and AO equals to B, and OC equals to 2B. So in total, OC will be equal to B plus 2B. B plus 2B equals to 3B. So AC equals to 3B, and AC square will be equal to 3B square, equals to AD square. AD equals to 4. So AD square is 4 square. 4 square is 16, plus DC square. DC is equals to 6, so DC square is 6 square. 6 square is 36. So in total we got that 3B square equals to 16 plus 36. 16 plus 36 is 52, so I write it down. So we got that 3B square equals to 52. Now I will take the root out of this equality. We will get that 3B equals to the root of 52. Okay? We took a root out of this equality. We got that 3B equals to the root of 52. But 52 equals to 13 times 4. And we can split the root. If we have root of A times B, the root of A times B equals to the root of A times root of B. Here we can write that 3B equals to the root of 4 times the root of 13. Okay? We splitted the root of 52 to 2 roots. Okay? The root of 4 is 2, so I write it down. Maybe equals 2 times root 13. We got that 3B equals 2 times the root of 13. We will divide this equality by 3 in order to get the value of B. We will get that B equals to 2 over 3 times root 13. Will be equals 4 over 3 times root 13. Okay, so we divided this equality by 3, we got that B equals to 2 over 3 times root 13, and if B equals to 2 over 3 times root 13, then 2 times B will be equal to 4 over 3 times root 13. Okay, so we can write here that b equals to 2 over 3 times root 13, and 2 times b equals to 4 over 3 times root 13. Okay, so we found out the value of b and 2b. We'll do the same process on the other side, because we know that angle ADC is a right angle. It equals to 90 degrees. So if angle ADC is a right angle, then triangle ADC is a right triangle. So we can implement the Pythagorean theorem in the right triangle ADC. Okay? We can implement the Pythagorean theorem in this right triangle ADC. So, according to the Pythagorean theorem, the square of the hypotenuse, that is to say AC square, equals to the sum of the squares of the perpendiculars, equals to AD square actually we've already done this process, and we found that b equals to 2 over 3 times root 13, while 2b equals to 4 over 3 times root 13. Okay, so actually the other side is here. We know that angle BCD equals to 90 degrees. It is a right angle. Angle BCD equals to 90 degrees. So if this angle BCD equals to 90 degrees, then triangle BCD is a right triangle. In the right triangle BCD, you can implement the Pythagorean theorem that states that the square of the hypotenuse, that is to say dB square, equals to the sum of the squares of the perpendiculars, equals to DC square plus BC square. Okay, so we actually implemented the Pythagorean theorem in the right triangle BCD. According to the Pythagorean theorem, the square of the hypotenuse, that is to say dB square equals to DC square plus BC square equals to DC square plus BC square. That is the sum of the squares of the perpendiculars. Okay, but what is the value of dB? The value of dB is dO plus OB. dO plus OB is the value of dB. Okay, but dO equals to A and OB equals to 2A. So in total the value of dB will be equal to A plus 2A. That is to say dB equals to 3A. If dB equals to 3A, then dB square will be equal to 3A square, and all equals to DC square. DC equals to 6 units, so DC square will be equal to 6 square. 6 square is 36, plus BC square. BC equals to 8 units, so BC square is 8 square, and 8 square is 64. So in total we got that 3 times A square equals to 36 plus 64. 36 plus 64 equals to 100, so I write it down. So we got that 3 times A squared equals to 100. Okay, 3 times A squared equals to 100. Now we'll take a root out of this equality, and we'll get that 3A equals to the root of 100. The root of 100 is 10. So we can write down that 3A equals to the root of 100, or 3A equals to 10. 3A equals to 10, so we can divide this equality by 3 in order to get the value of A. Okay, so we get that A equals to 10 over 3 units, and 2A equals to 20 over 3 units. Okay, we divided this equality by 3, and we got that A equals to 10 over 3 units. And if A equals to 10 over 3 units, then 2 times A will be equal to 20 over 3 units. Okay, so we can write here that A equals to 10 over 3 units, and 2 times A equals to 20 over 3 units. Okay, in the next step we'll copy this drawing to this page. Without A and B, we will only write down the values of A and B that we have already found. Okay, so I will draw again the same drawing. We found that AO equals to 2 over 3 times root 13, and OC equals to 4 over 3 times root 13. And OD equals to 10 over 3 units, while OB equals to 20 over 3 units. Okay, so we actually found out the values of all the line segments inside this circle. In the next step, we will extend line segment AC until it touches the circle at point P. Okay, we will extend line segment AC till it touches the circle at point P. So actually P is the point of contact between the circle and chord AP. Again, P is the point of contact between the circle and chord AP. And we'll find out the value of the new line segment CP according to a new rule, rule number 4. Actually, rule number 4 states that if two lines are intersecting each other, if two chords are intersecting each other, we have here chord AB. This is chord AB that intersects with chord CD. This is chord CD. So chord AB, the red color, intersects with chord DC in the black color, and the point of intersection is point O. This is the point of intersection, point O. Then, if this is the data that we have, then the following equality is true, that OA times OB equals to CO times DO, or AO times OB, AO times BO equals to CO times DO. Okay. Again, if two chords, chord AB and chord CD, are intersecting each other and the point of intersection is point O, then the following equality is true, that AO times BO equals to CO times DO. Again, AO times BO equals to CO times DO. So we can write down rule number 4. So rule number 4 states that if two chords that is to say chord AB and chord CD are intersecting each other at point O. Point O is the point of intersection between chord AB and chord CD. If two chords are intersecting each other at point O, then the following equality is true. That AO times BO equals to CO times DO. So I will read rule number 4 again. Rule number 4 states that if two chords, that is to say chord AB and chord CD, are intersecting each other at point O. Point O is the point of intersection between chord AB and chord CD. Then the following equality is true, that AO times BO equals to CO times DO. AO times BO equals to CO times DO. Okay, so we actually can implement rule number 4 in our circle, because we have in our circle chord AP that intersects with chord DB at point O. Again, chord AP intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DB. Okay, I will write it down. Chord AP intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DB. Therefore, according to rule number 4, AO times OP equals to DO times OB. Again, AO times OP equals to DO times OB. So write it down. AO times OP equals to DO times OB. So I will read again the fixes they wrote. Chord AP intersects with chord DB at point O. Chord AP intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DB. Therefore, according to rule number 4, AO times OP equals to DO times OB. Therefore, according to rule number 4, AO times OP equals to DO times OB. Again, AO times OP equals to DO times OB. Okay, so AO equals to 2 over 3 times root 13. And OP equals to OC plus CP. OP equals to OC plus CP. All equals to DO. DO is 10 over 3 units. Times OB. OB is 20 over 3 units. So in total we got that 2 over 3 times root 13 times OC plus CP, that is OP equals to OC plus CP equals to 10 over 3 times 20 over 3 units. here, okay, so what is the value of OC? The value of OC is 4 over 3 times root 13 units, so I write it down. Okay, so I substituted OC by 4 over 3 times root 13. In total we got the 2 over 3 times root 13 times 4 over 3 times root 13 plus CP equals to 10 over 3 times 20 over 3. Here we have 3 in the denominator of this side of the equation, and we have 3 in the denominator of the other side of the equation, so we can cancel 3. Okay, we can cancel 3. So after we cancel 3, we get that 2 times root 13 times 4 over 3 times root 13 plus CP equals to 10 times 20 over 3. Okay, so actually here we have 2 times root 13 times 4 over 3 times root 13. So root 13 times root 13 is 13, and 2 times 4 is 8. So I will write it down. So 2 times 4 is 8, and root 13 times root 13 is 13. In total we will get that 8 times 13 over 3. Okay, 8 times 13 over 3, and here we have 2 times root 13 times CP. Okay, 2 times root 13 times CP equals to 10 times 20 over 3. 8 times 13 is 104, so I write it down. So 8 times 13 is 104 over 3, and 10 times 20 is 200, so I write it down. So in total we got that 104 over 3 plus 2 times root 13 times CP equals to 200 over 3. Now we'll subtract 104 over 3 from both sides of the equation. We'll get that 2 times root 13 here is subtracted 104 over 3 from both sides of the equation. 104 over 3 minus 104 over 3 is 0, so we left only with 2 times root 13 times CP, and 203 over 3 minus 104 over 3 is 200 over 3 minus 104 over 3. Okay? Now we'll take a common factor of 3 in the denominator of this side of the equation. We'll get that so here we took a common factor 3 in the denominator of this side of the equation, so we got that 200 minus 104 over 3 equals to 2 times root 13 times CP. 200 minus 104 is 96, so I'll write it down. So in total we have 2 times root 13 times CP equals to 96 over 3. 96 over 3 is 32, so I write it down. We got that 2 times root 13 times CP equals to 32. We'll divide this equality by 2. We will get that root 13 times CP equals to 16. 32 over 2 is 16. We divide this equality by root 13 in order to get the value of CP. We'll get that CP equals to 16 over root 13 units. Okay, here we divided this equality by root 13 and we got that CP equals to 16 over root 13 units. Okay, so we write here that CP equals to 16 over root 13 units. Okay, we got the value of CP. Okay, in the next step we will extend line segment DC until it touches the circle at point Q. Okay. So we extended line segment DC until it touches the circle at point Q. Q is the point of contact between the circle and chord DQ. Again, Q is the point of contact between the circle and chord DQ. We'll find the value of the new line segment CQ according to rule number 4. Actually, according to rule number 4, we can use rule number 4 because we have chord DQ that intersects with chord AP at point C. Chord DQ intersects with chord AP chord DQ intersects with chord AP at point C. Point C is the point of intersection between chord DQ and chord AP. So according to rule number 4, therefore according to rule number 4, AC times CP equals to DC times CQ. Again, AC times CP equals to DC times CQ. So I will read the things that I wrote again. Chord DQ intersects with chord AP at point C. Chord DQ intersects with chord AP at point C. Point C is the point of intersection between chord DQ and AP. Therefore, according to rule number 4, AC times CP equals to DC times CQ. Therefore, according to rule number 4, AC times CP equals to DC times CQ. Again, AC times CP equals to DC times CQ. Okay. AC equals to 2 over 3 times root 13 plus 4 over 3 times root 13. In total, AC equals to 6 over 3 times root 13. CP, we've already found that the value of CP is 16 over root 13 units. All equals to DC equals to 6 units, and CQ is the line segment that we want to find out the value of it, so we will leave it as it is. So in total we got that 6 over 3 times root 13 times 16 over root 13 equals to 6 CQ. 6 over 3 is 2, and root 13 over root 13 is 1, because of the fact that we have root 13 in the numerator and root 13 in the denominator of this side of the equation. Root 13 is cancelled. Okay, root 13 is cancelled, or root 13 over root 13 is 1, and 6 over 3 is 2. So I write it down. So we got that 2 times 16 equals to 6 CQ. 2 times 16 is 32, so I write it down. So we got that 32 equals to 6 CQ. We divide this equality by 6 in order to get the value of CQ. So we divided this equality by 6, and we got that CQ equals to 32 over 6. We can take a common factor 2 from the, or we can divide the numerator of this number 13 over 6 by 2, and the denominator, we can divide also the denominator by 2. Okay, so we'll get that CQ equals to 16 over 3 units. We divided the numerator and the denominator of this number 13 over 6 by 2. We got that CQ equals to 16 over 3 units. Okay, so CQ equals to 16 over 3 units. In the next step, we will extend line segment BC until it touches the circle at point R. So we extended line segment BC until it touches the circle at point R. Point R is the point of contact between the circle and chord BR. Again, point R is the point of contact between the circle and chord BR. Okay, and we will find out the value of RC by implementing the fourth rule in this circle. We have chord BR that intersects with chord DQ at point C. Okay, I'll write it down. Chord BR or chord RB intersects with chord DQ, chord RB intersects with chord DQ at point C. Point C is the point of intersection between chord RB and chord DQ. Again, chord RB intersects with chord DQ at point C. Point C is the point of intersection between chord RB and chord DQ. Therefore, according to rule number 4, RC times BC equals to DC times CQ. Again, RC times BC equals to DC times CQ. So I read again the fix that I wrote. Chord RB intersects with chord DQ at point C. Chord RB intersects with chord DQ at point C. Point C is the point of intersection between chord RB and chord DQ. Therefore, according to rule number 4, RC times BC equals to DC times CQ. Again, RC times BC equals to DC times CQ. Okay, so we got that RC times BC, BC is 8 units, equals to DC, DC is 6 units, times CQ, CQ is 16 over 3 units. So in total we got that 8 times RC equals to 6 times 16 over 3. 6 over 3 is 2, so I write it down. In total we got that 8 times RC equals to 2 times 16. 2 times 16 is 32, so I write it down. So we got that 8 times RC equals to 32. We divide this equality by 8 in order to get the value of RC. 32 over 8 is 4, so RC equals to 4 units. Again, we divided this equality by 8, so RC equals to 32 over 8, 32 over 8 is 4, so we got that the value of RC is 4 units. RC equals to 4 units. Okay, so we actually got the values of all the line segments inside the circle, and the only missing thing is the radius of this circle. In order to find out the radius of this circle, we will implement rule number 5, new rule, in this circle. According to rule number 5, if two chords are intersecting each other at 90 degrees, for example, we have chord AB that intersects with chord CD, at 90 degrees. So chord AB intersects with chord CD at 90 degrees. At the point of intersection, they create 90 degrees between them. And the point of intersection will be defined as point O. Okay? So, if this is the data that we have, then the following equality is true. That 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. Okay? 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. Okay, so I'll write rule number 5. According to rule number 5, if two chords are intersecting each other at 90 degrees, two chords, that is to say chord AB and chord CD, at 90 degrees, and the point of intersection is point O, then the following equality is true. that 4 times the radius of this circle squared equals to a all square plus b all square plus c all square plus d all square. So I will read rule number 5 again. If two chords, that is to say chord AB and chord CD, are intersecting each other at 90 degrees, those two chords AB and CD create 90 degrees at the point of intersection, and the point of intersection is point O. So if this is the reality, if this is the data that we have, then the following equation is true. The following equality is true, that 4 times the radius of the circle squared equals to a all square plus b all square plus plus c all square plus d all square. Okay, 4 times the radius of this circle squared equals to a all square plus b all square plus c all square plus d all square. Okay, so whenever you have two chords that are intersecting each other at 90 degrees, then you can implement rule number 5 that states that 4 times the radius of this circle squared equals to a all square plus b all square plus c all square plus d all square. Okay, we can actually implement rule number 5 in our circle. First of all, we know that angle BCD is a right angle, it equals to 90 degrees. It is given us in the question that angle BCD equals to 90 degrees. Angle BCD is a right angle, equals to 90 degrees. And chord RB intersects with chord DQ at 90 degrees, because all the angles here around point C are right angles, they are 90 degrees. Okay, chord RB intersects with chord DQ at 90 degrees. And the point of intersection between chord RB to chord DQ is point C. Therefore, according to rule number 5, RC times CB and 4 times the, according to rule number 5, 4 times the radius of this circle squared equals to RC square plus BC square plus DC square plus CQ square. Okay, so I'll read the things that I wrote. Angle BCD equals to 90 degrees. It is given us in the question that this angle BCD is a right angle, it equals to 90 degrees. And chord RB intersects with chord DQ at 90 degrees. Chord RB intersects with chord DQ at 90 degrees. And the point of intersection is point C. Okay? Therefore, according to rule number 5, 4 times the radius of this circle squared equals to RC square plus BC square plus DC square plus CQ square. Again, 4 times the radius of this circle squared equals to RC square plus BC square plus DC square plus CQ square. Okay, so we got that 4 times the radius of the circle squared equals to RC squared. RC equals to 4 units, so RC squared is 16 plus BC squared. BC equals to 8 units, so BC squared is 8 squared. 8 squared is 64 plus DC squared. DC equals to 6 units, so DC squared is 6 squared. 6 squared is 36 plus CQ squared. CQ equals to 16 over 3 units, that is 3 third units, so 3 third units squared is 28.444. So in total we got that 4 times the radius of the circle squared equals to 16 plus 64 plus 36 plus 28.444. Now 64 plus 36 equals to 100, and 100 plus 16 is 116, and 116 plus 28.444 equals to 144.444. So I write it down that in total we got that 4 times the radius of the circle squared equals to 144.444. Okay, we got that 4 times the radius of the circle squared equals to 144.444. Now we will divide this equality by 4 in order to get the value of r squared. We will get that r squared equals to 36.111. Okay, we divided this equality by 4, we got that r squared equals to 36.111. Okay, so I write that r squared equals to 36.111. But we know that the area of any circle equals to pi times the radius of the circle squared. Okay, the area of any circle, the formula for the area of any circle is pi times the radius of that circle squared. and we know that r squared equals to 36.111, so we can substitute r squared in the formula of the area of a circle by 36.111, and we will get that the area of our circle equals to pi times the radius of the circle, pi times the area of the circle equals to pi times r squared, and r squared is 36.111 units. So the area of the circle equals to pi times 36.111 square units. Okay. So actually found out that the area of the circle equals to pi times 36.111 square units, or in terms of numbers, the area of the circle equals to 113.45 square units. Okay, so the final answer is that the area of the circle equals to 113.45 square units. Again, the area of this circle equals to 113.45 square units. Okay, now I'll summarize the lecture. Actually, we wanted to find out the area of this circle, and we know that inside the circle we have a shape, and we have inside the shape, this angle is a right angle, and also this angle is a right angle. Side BC of this shape is 8 units, side DC of the shape is 6 units, and side AD of this shape is 4 units, and we want to find out the area of this circle. Okay? So in order to find out the area of this circle, we must define the term of one-sided angles. What are one-sided angles? Actually, if we have line A and line B, and line C intersects those two lines A and B, angles alpha and beta are defined as one-sided interior angles. Okay, angles alpha and beta are defined as one-sided interior angles, and the reason that they are defined as one-sided angles is because of the fact that angles alpha and beta both are located at the right side of line C. They are to the right of line C, both of them. So both of them are the same side of line C. For that reason, they are defined as one-sided angles, because both of them at one side of line C. For that reason, they are defined one-sided angles. Both of them are located at the right side of line C. For that reason, they are defined one-sided angles. And they are also interior angles because both of them are located inside the structure of lines ACB. They are both located inside this structure of lines ACB. For that reason, they are defined as interior angles. And we also have the second type of one-sided angles. Those two angles, alpha and beta, are defined as one-sided exterior angles. Again, they are one-sided angles because they are located at the same side of line C. They are both located at the right side of line C. For that reason, they are defined as one-sided angles, and because of the fact that they are both angles are located outside of this structure of lines ACB, they are outside of this structure of lines ACB, they are defined as exterior angles. Okay, so we actually have a rule number 1 about one-sided angles. According to rule number 1, if the sum of the two one-sided angles, and it doesn't matter if they are interior one-sided angles or exterior one-sided angles, if the sum of those two one-sided angles equals to 180 degrees, then line A is parallel to line B. So actually here, if we know that the sum of those two angles is equal to 180 degrees, then we can deduce from it, according to rule number 1, that line A is parallel to line B. Again, if alpha plus beta equals to 180 degrees, then according to rule number 1, line A is parallel to line B, or those two lines A and B are parallel to each other. And the same rule applies to one-sided interior angles. If we know that the sum of those two angles, alpha and beta, is equal to 180 degrees, then we can deduce from it, according to rule number 1, that line A is parallel to line B, or lines A and B are parallel to each other. So if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Okay, so we implemented rule number 1 in our circle, because in our circle we have two angles, angle ADC and angle BCD. Both those two angles are right angles, and they are actually interior one-sided angles, because you can view AD as line A BC is line B, and DC is line C that intersects line A and B, and the point of intersection with BC is C, and the point of intersection with AD is D. So actually those two angles are inside the structure of lines of this structure. For that reason they are defined as one-sided interior angles, and they are one-sided angles because both of them are located at the right side of line segment DC, and you can view DC as line C in our example. So they are defined as one-sided interior angles, and the sum of those two angles equals to 180 degrees. So according to rule number 1, line segment AD is parallel to line segment BC. AD is parallel to BC. Okay? And then we define the theorem of vertex angles. If we have two lines that are intersecting each other, and this is the point of intersection, they create four angles: angle 1, angle 2, angle 3, and angle 4. And actually angle 1 and 3 are defined as vertex angles, and according to rule number 2 they are equal to each other, and also angles 2 and 4 are defined as vertex angles, and according to rule number 2 they are equal to each other. Okay, so we have rule number 2 that states that vertex angles are equal to each other. So we have two types of vertex angles. This is the first pair of vertex angles that are equal to each other according to rule number 2, and those angles are the second type of vertex angles that they are also equal to each other according to rule number 2. So we actually implemented rule number 2 in our circle because first of all we have those we have those two angles that are equal to each other. They are defined as vertex angles, and according to rule number 2 they are equal to each other. Okay, and then we define the theorem of alternating angles. Actually, if we have lines A and B and line C that intersects lines A and B, and actually those two angles alpha and beta are defined as interior alternating angles. They are alternating angles because they are located at different sides of line C. Okay, as you have remember, while one-sided angles are located at the same side of line C, alternating angles are located at different sides of line C. Okay, so that is the distinction between one-sided angles and alternating angles. While one-sided angles are located at the same side of line C, alternating angles are located at different sides of line C. While angle alpha is located at the left side of line C, angle beta is located at the angle alpha is located at the right side of line C, and angle beta is located at the left side of line C. So because of the fact that they are located at different sides of line C, they are defined as alternating angles, and because of the fact that they are located inside of this structure of lines ACB, they are defined as interior angles because they are inside of this structure of lines ACB. Okay, and we have the second type of alternating angles. Those angles alpha and beta are defined as exterior alternating angles. Again, they are alternating angles because they are located in different sides of line C, while angle alpha is located at the right side of line C, angle beta is located at the left side of line C. So because of the fact that they are located in different sides of line C, they are defined as alternating angles. Okay, and they are exterior angles because they are located outside of this structure of lines ACB. For that reason, they are defined as exterior angles. Okay, and we have a rule for alternating angles. Rule number 3, according to rule number 3, alternating angles, and it doesn't matter if they are interior alternating angles or exterior alternating angles, alternating angles between parallel lines are equal to each other. When I say parallel lines, it might be parallel lines or parallel line segments. It is the same. It can be also parallel line segments. Okay, it is not only lines, but it includes also line segments. Okay, alternating angles between parallel lines are equal to each other. So if we know that line A is parallel to line B, then according to rule number 3, angle alpha equals to angle beta. Okay, if we know that line A is parallel to line B, then according to rule number 3, angle alpha and angle beta are equal to each other. Okay, and the same rule applies to interior alternating angles. If we know that line A is parallel to line B, if those two lines are parallel to each other, then according to rule number 3, angle alpha equals to angle beta. Okay, so we actually implemented rule number 3 in our circle. First of all, we have already proved that those two angles are vertex angles, and according to rule number 2 they are equal to each other. And also then we have those two angles, they are alternating angles because they are located at different sides of line segment AC, and they are located between parallel line segments. Line segment AD is parallel to line segment BC. So we have alternating angles that are located between parallel line segments. Therefore, according to rule number 4, they are equal to each other. Okay? And those two angles are also equal to each other because they are alternating angles. They are located at different sides of line segment BD, and they are also located between parallel line segments. Line segment BC is parallel to line segment AD. So according to rule number 3, they are equal to each other. So we actually proved that 3 angles of this green triangle are equal to 3 angles of this right triangle, of this green triangle, because we proved that those two angles are equal to each other, and those two angles are also equal to each other, and those two angles are also equal to each other. So 3 angles of this green triangle are equal to 3 angles of this green triangles, So we actually proved that those two green triangles are similar to each other. Triangle BOC is similar to triangle AOD. According to the rule that angle, if you prove that three angles of one triangle are equal to three angles of the other triangle, actually prove that those those two triangles are similar to each other. So if you have two triangles that are similar to each other, if triangle ABC is similar to triangle DEC, then we have the following relationship between their sides, that side AB over side DE equals to side AC over side DF, that equals to side BC over side EF. Okay, so we implemented this rule in our circle, in our two similar triangles. We said that OB over OD equals to OC over OA and equals to BC over AD. Okay, OB over OD equals to OC over OA equals to BC over AD. But we know that the value of BC is 8 units and the value of AD is 4 units. So we can substitute BC by 8 and AD by 4. And 8 over 4 is 2. So we have here big equality. We can divide it, we can separate it to small equalities. The first equality will be OB over OD equals to 2. If OB over OD equals to 2, then if we multiply this equality by OD, we will get that OB equals 2 times OD. OB is twice as large as OD. So if OD equals to A, then OB that is twice as large as OD will be equal to 2A. OA equals to A, OB must be equal to 2 times A. Okay, and we derive the second equality from this big equality. The second equality is that OC over OA equals to 2. If OC over OA equals to 2, then if we multiply this equality by OA, we will get that OC equals to 2 times OA. So OC is twice as large as OA. So if OA equals to B, then OC must be equal to 2 times B, because OC is twice as large as OA. So if OA equals to B, then OC will be equal to 2 times B. Okay, so in order to find out the values of A and B, we implemented the Pythagorean theorem. Actually, we have angle ADC. It is given us that it is equal to 90 degrees. It is given us in the question. So if angle ADC is a right angle, then triangle ADC is a right triangle. So we can implement the Pythagorean theorem in the right triangle ADC. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in any right triangle. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ADC, the square of the hypotenuse is AC square, will be equal to AD square plus DC square. Okay, in the right triangle ADC, AC square will be equal to AD square plus DC square. But what is the value of AC? The value of AC is OA plus OB, and OA equals to B, and OB equals to, and OC equals to 2B. So OA plus OC will be equal to B plus 2B. B plus 2B is 3B, so AC equals to 3B. So AC square is 3B square. and AD equals to 4, so AD squared will be equal to 4 squared is 16, DC equals to 6, so DC squared is 6 squared, is 36, so the only missing variable is B. We solved this simple equation and we got that B equals to 2 over 3 times root 13, while 2 times B equals to 4 over 3 times root 13. Okay, in the next step, we actually know that angle BCD is a right angle, it equals to 90 degrees. If angle BCD is a right angle, then triangle BCD is a right triangle, so we can implement the Pythagorean theorem in the right triangle BCD. According to the Pythagorean theorem, the square of the hypotenuse, that is to say dB square, equals to the sum of the squares of the perpendiculars, equals to DC square plus BC square. Okay, we got that dB square equals to DC square plus BC square. Okay, and we know that the value of dB equals to OD plus OB, and if OD equals to 8, then OB equals 2 times A, so in total dB equals to A plus 2A, A plus 2A is 3A, so dB equals to 3A, so dB square will be equal to 3A squared. We have the value of DC and BC. So we put this in the equation. We got that A equals to 10 over 3 units and 2A equals to 20 over 3 units. So we actually know the values of all the line segments inside this circle. I copied this drawing to this page, and in the next step we actually extended line segment AC until it touches the circle at point P. Point P is the point of contact between the circle and chord AP. And in order to find out the value of line segment CP, we implemented rule number 4 in our circle. According to rule number 4, if two chords, that is to say chord AB and chord DC, are intersecting each other at point O is the point of intersection between chord AB and chord DC. So if this is the data that we have, then the following equality is true, that AO times BO equals to CO times DO. AO times BO equals to CO times DO. Again, rule number 4 states that if two chords are intersecting each other at point O, then the following equality is true, that AO times BO equals to CO times DO. So we actually implemented rule number 4 in our circle because we have chord AP that intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DB. So according to rule number 4, AO times OP will be equal to DO times OB. Okay, AO times OP will be equal to DO times OB. Okay, and okay, AO times OP equals to DO times OB. But so we have the values of all the line segments inside this equality. The only missing line segment is CP. We put the data inside this equality and we found out that the value of CP equals to 16 over root 13 units. Okay, this line segment CP equals to 16 over root 13 units. And in the next step, next phase, we extended line segment DC until it touches the circle at point Q. Point Q is the point of contact between the circle and line segment DQ. And in order to find out the value of line segment CQ, we implemented rule number 4. We have chord DQ that intersects with chord AP at point C. Point C is the point of intersection between chord DQ and chord AP. So according to rule number 4, AC times CP equals to DC times CQ. Again, AC times CP equals to DC times CQ. Okay? AC times CP equals to DC times CQ. And again, we have all the values of all the line segment except CQ. We put the data inside this equality and we found out that the value of CQ is 16 over 3 units. Okay, this line segment CQ equals to 16 over 3 units. And then we extended line segment BC until it touches the circle at point R. Point R is the point of contact between the circle and line segment RB. Between the point R is the point of contact between the circle and chord BR. And according to rule number 4, we have chord RB that intersects with chord DQ at point C. Again, chord RB intersects with chord DQ at point C. So according to rule number 4, RC times BC equals to DC times CQ. Again, RC times BC equals to DC times CQ. RC times BC equals to DC times CQ. Okay, the only missing line segment is RC. We put the data inside this equality and we found out that the value of RC is 4 units. So we actually have all the line segments inside this circle, the values of all the line segments inside this circle, and the only missing thing is the radius of this circle. And in order to find out the value of the radius of this circle, we implemented rule number 5 in this circle. According to rule number 5, if two chords are intersecting each other at 90 degrees, if the point of intersection, point O, they create 90 degrees between them, then the following equality is true, that 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. Okay, so I'll read rule number 5 again. If two chords are intersecting each other at 90 degrees at point O is the point of intersection. You have two chords called AB and chord CD that are intersecting each other at 90 degrees at point O, then the following equality is true, that 4 times the radius of the circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. So actually implemented rule number 5 in our circle. First of all, we know that angle BCD is a right angle, it equals to 90 degrees. Actually all the angles around point C are right angles. So we have chord RB that intersects with chord DQ at 90 degrees, and the point of intersection between chord RB and chord DQ is point C. So according, we can implement rule number 5 because we have two chords that are intersecting each other at 90 degrees. So according to rule number 5, 4 times the radius of this circle squared equals to RC square plus BC square plus DC square plus CQ square. Okay, 4 times the radius of this circle squared equals to RC square plus BC square plus DC square plus CQ square. Okay, and we know all the values of all the line segments here. The only missing variable is R, so we put the data inside this equality, and we found out that the radius of this circle equals to 36.111 units. Okay, and we know that the area of any circle equals to pi times the radius of the circle squared. So we can substitute r squared by 36.111 because r squared equals to 36.111. And we found out that the area of our circle equals to pi times 36.111 square units. Or in terms of numbers, the area of our circle equals to 113.45 square units. Again, the area of this circle equals to 113.45 square units. Okay, thank you very much.